Hello students and welcome. If you're getting ready for your SSLC chemistry exam, you are in exactly the right place. In this explainer, we're going to crack a code that's right at the heart of chemistry. A puzzle that, once you solve it, will completely change how you see the periodic table.
You've seen this chart so many times, right? It's this incredible masterpiece of organization. All the elements are neatly arranged in their little boxes. But have you ever really stopped and wondered why it has this specific shape? What are the secret rules that decide exactly where each element goes?
This question. This is one of the biggest head-scratchers in chemistry. But you know what? The answer is the key to understanding the entire table. By the time we're done here, you'll know exactly why this happens. And even better, you'll know how to use that rule to find any element's address on the table, a skill that is absolutely essential for your exam.
Okay, let's get into it. First, we'll look at the puzzle itself, using potassium as our example. Then, we're going to go deeper than just shells and talk about subshells. After that, we'll learn the rules for filling up those subshells with electrons. Next, we'll use those rules to decode an element's address. And finally, we'll see how that all connects to classifying elements. Let's begin.
So, let's start with an element you probably know pretty well, potassium. Its symbol is K and its atomic number is 19. That means we have 19 electrons that we need to find a home for.
Now, if we use the simple shell model you first learned, we start filling things up. Okay, 2 electrons go in the first shell, the K shell. 8 electrons go in the second one, the L shell. Now that leaves us with 9 electrons, so you'd think the configuration would be 2, 8, 9, right? But the actual configuration for potassium is 2, 8, 8, 1. And that's our puzzle.
And this is the real heart of the mystery. We know for a fact that the third shell, the M shell, has room for 18 electrons. So why on earth does that last 19th electron decide to jump all the way out to the fourth shell, leaving the third one incomplete? Well, the answer is hidden in a more detailed picture of what these shells actually look like.
To really get a handle on the modern periodic table and to solve our potassium mystery, we need to zoom in a little closer. We need to go one level deeper than just shells. We have to talk about something called subshells. Here's an easy way to think about it. If a shell is like a floor in a big apartment building, then the subshells are like the different types of apartments on that floor. They're these separate areas within each main energy level, and they have names: S, P, D, and F. And look, there's a really simple, elegant pattern here. The first shell just has one subshell, an S subshell. The second shell has 2, S and P. The third shell has 3, S, P, and D. And the fourth has 4. You see the rule, right? The shell number is the same as the number of subshells it has. Pretty neat.
Now, these subshells are made up of things called orbitals, which are just the specific 3D spaces where you're most likely to find an electron. And as you can see, they have very different shapes. The S orbital is a nice simple sphere, but the P orbitals are shaped more like dumbbells.
Okay, this part is super important for your exam, so listen close. Each type of subshell has a strict limit on how many electrons it can hold. An S subshell can hold a maximum of 2 electrons. A P subshell holds 6, and a D subshell can hold up to 10. You'll definitely want to commit these numbers to memory.
So, here's the deal. Knowing what subshells are and how many electrons they hold is great, but it's only half the story. The real secret, the key to everything, is knowing the order in which the electrons fill them up.
This is it. This is the single most important rule you need to remember. Maybe even write it down. Electrons fill up the subshells based on their energy level, from lowest to highest. It's not about filling the first shell, then the second, then the third. See, nature is efficient. Electrons will always go to the lowest energy spot available, no matter which main shell it happens to be in.
This diagram, this is your secret weapon for the exam. It shows you the exact order to fill electrons based on their energy. All you have to do is follow the diagonal arrows, starting from the top. Now look closely. See how the arrow hits 4s right after it hits 3p, but then it goes back to 3d? That's the whole trick right there. This diagram tells us that the 4s subshell is actually at a lower energy level than the 3d subshell. If you just follow those arrows, you will always get the order right. The sequence goes 1s, then 2s, then 2p, and 3s, then 3p, and then here's that crucial part. It jumps to 4s before it loops back to fill up the 3d subshell. All right, we've got the master rule now. So let's put it to the test.
let's finally solve that potassium puzzle, and when we do, you'll see how this configuration thing is basically a GPS coordinate for an element on the periodic table.
Okay, let's place all 19 of potassium's electrons using our new energy rule. Ready? 2 go in 1s, 2 more in 2s, 6 fill up 2p. So far, that's 10 electrons. Then 2 in 3s, and 6 in 3p. We're at 18 electrons now. So, where does that very last 19th electron go? Well, according to our energy diagram, the next lowest spot after 3p is 4s. So that last electron goes right into the 4s subshell. And just like that, the mystery is solved. The electron is in the 4th shell because the 4s subshell has less energy than the 3d subshell.
Now this is the really amazing part. That configuration we just wrote isn't just some boring list of electrons, it is the element's exact address in the periodic table. Let's look at potassium's again. The highest shell number, which is 4, that tells you the period. So potassium is in period 4. The subshell where that very last electron landed, S, that tells you the block, so it's an S block element. And from there, finding the group is easy.
So let's see how this all comes together to build the entire structure of the periodic table. It's this direct link, this connection between an element's electron configuration and where it lives on the table that makes the whole thing such a powerful tool.
And this table here just lays out the simple rules for finding the group number. Once you know the block, it's a piece of cake. For S-block elements, like our friend potassium, the group number is just the number of electrons in that outer S subshell. Potassium's configuration ends in 4s1, so it's in group 1. For P-block elements, you just add 12 to the number of outer P electrons. It's all based directly on the configuration.
So, here it is. This is your main takeaway for the exam. If you can write the subshell electronic configuration for an element, and you can, then you can find its exact location, no problem. The highest shell number gives you the period, the last subshell filled gives you the block, and the simple block rule gives you the group. It's a perfect system. This is the big idea I want you to leave with. That configuration isn't just some random exercise. It's the secret code that explains why the periodic table is shaped exactly the way it is. The configuration tells you the position, and the position tells you all about the element's properties.
With this knowledge, the periodic table completely changes. It's not just a chart of facts you have to memorize anymore. It's a logical map that you can actually read and understand. You now have the key to unlock all its secrets. Good luck with your exams!